Hello, I'm Richard Grisenthwaite, ARM's Chief Architect, and in this presentation I'm going to give a brief introduction to a research programme called Morello, which we are doing in conjunction with UKRI. Morello is bringing in the concepts from the University of Cambridge's CHERI architecture into a prototype version of the ARM architecture and making that available for researchers. Now, Robert Watson at this event is talking about the details of CHERI, and I'm not going to spend a lot of time going into that. But just to give a brief overview of the essentials of CHERI, it brings in a concept architecturally called capabilities, which are 128-bit quantities which can be held in special capability registers and held in memory. These capabilities comprise of addresses, bounds, and permission information. And the idea is these can be used in the same way as registers, when they're held in registers, so that you can do a load or a store using the capability as the address. And when that load or store happens, the address that's embedded inside the capability is compared against the bounds, and the permissions are checked that you're able to use to perform that form of operation on that capability. Similarly, when you do data processing with the capability registers, there are special rules enforced by the hardware which say that you cannot change the data or the contents of the capability arbitrarily. Instead, you have limits as what to do. In particular, you can't arbitrarily increase the bounds, you can merely reduce them. Similarly, you cannot increase your permissions, you can reduce it. And this allows you to say, I've been given a capability, I now want to reduce the scope of that and hand it on to somebody else. But if I'm given a capability, I cannot increase the scope and go elsewhere. And this then allows a provenance of capabilities that they can only be generated from another. The other key point that comes into the architecture for capabilities is this piece of metadata that sits alongside all of memory, which says whether each 128 bits contains either ordinary data or contains a capability. And the idea behind this is that only stores of explicit capabilities will be tagged as capabilities. And this makes it makes it actually impractical to be able to forge a capability by just writing in different data. If you write data into something that used to hold a capability, it stops being a capability. And this principle allows you to give a strong provenance of a capability only came from another capability and has no bigger permissions than that were held within its parent version. And this provides a strong continuity that can be used to build security structures on top of. In basic principle, capabilities are used in place of normal pointers in some or all situations. But exactly how that happens and where that happens is something that we are actually looking to explore as part of this research program. One option is to simply replace all pointers with capabilities, which would give potentially very strong spatial memory protection, but is a substantial ABI change, and we have concerns been raised about the impact on cache pressure and so on from that growth in the pointers. Why ARM is interested in capabilities is because we've been working with the university for some 4 or 5 years now on this concept, because security remains a fundamental challenge for all computing, and ARM wants to be at the front edge of pioneering new approaches to improve security if they really work. We believe that this capability architecture has the potential to be a very big step in addressing security based on a whole bunch of fundamental principles along the lines of the provenance of the capabilities I talked about before. In particular, capabilities can address spatial memory in a very robust manner, and we have some ideas of how this can be used for temporal safety as well. And it's been observed that temporal and spatial memory safety issues have been around for many years. It's been some 50 years since the first ever buffer overflow attack, and there's published research that says as a sort of consistent run rate over the last umpteen years, around about 70% of all described vulnerabilities in some way involve memory safety issues. But in addition, CHERI and capabilities have the potential to be a foundation for a new mechanism of compartmentalization, which is far cheaper than the abuse of the process model that people use today by using subsets of page tables to hold parts of an application to compartmentalize them. And the idea of also being able to take CHERI to address temporal memory safety, we see tremendous value in as well, because there's a lot of issues such as use after free. And it isn't just ARM that's interested in this. Many of ARM's software vendors have been looking at this technology and believe that it is a substantial step forward potentially for security. Companies like Google and Microsoft have said this is really exciting stuff. We'd like to explore it properly in a proper system where we can run real big heavy software workloads. And then they say, but tell me what the performance impact is going to be. And that's a bit of a how long is a piece of string question, because it depends an awful lot on how the software is used and exactly what the details are. And there are complex usage models that we don't fully understand, won't understand until people have tried using in software, but people won't try using in software until they got some hardware. And so you get a chicken and egg, which is, the hardware doesn't get built until we got justifying software. The justifying software cannot be constructed till you've got compelling hardware. So this is all a novel thing. We want to go and learn about it. It's potentially a big step forward in security, but we need to do this research. And to give an idea of what some of the performance questions are associated with this, the whole spatial memory protection of CHERI involves replacing some or all of the pointers with capabilities, and that will have cache pressure. And one of the questions is, do you do all of the pointers, or do you just do some of them? Do you combine them with some base register and some 32-bit or 64-bit offsets? And that might be a very good model for Java or JavaScript, for example. There's a whole set of details there that require exploration. There are also questions about how a tag's held in memory. And this idea of this tag that tells you whether it's a capability or a piece of data is a piece of metadata that has to live in memory somehow, and it needs to be cached out in the system. And there's quite a lot of performance trade-offs and performance effects that are very hard to really understand and explain what this will mean for real software until you've got a real implementation of doing it. I talked about how CHERI can be used as a mechanism for improved compartmentalization, or as a tool for improved compartmentalization. But exactly what the performance wins are from doing that compared with using the current model is completely unclear, because people haven't got the hardware to go and experiment. And we want to do A versus B comparisons between current state-of-the-art techniques and using capabilities to say this can make it go faster, or this can give you more security for the same performance cost. And we simply haven't got a vehicle to allow that sort of detailed performance. And similarly, when we look at the temporal memory safety, we need to understand what are the real performance costs associated with that in a real system for real big workloads rather than just toy workloads. And the big question behind all of this is, how do these techniques running on this new architecture compare with today's established technology? Is any of this actually worth deploying? That is the fundamental question. And so in order to be able to do this, partly funded by the UK government through UKRI, and working in conjunction with a number of our major partners such as Microsoft and Google, we are developing the Morello board, which is an industrial demonstrator of a capability architecture. It comprises a set of CPUs which have built into them a prototype version of a capability architecture that's been put into the ARM architecture. Now, actually, that prototype version of the architecture is a superset of what we actually imagine would be commercially deployable. And we put in a superset, which is a really unusual thing to do, precisely to allow different approaches of using capabilities to be tried out and compared and contrast. And the feedback we get from that will then determine what we end up industrially deploying as and when we go forward with this technology. The idea here is to permit and encourage a whole bunch of software experimentation about using capabilities. And another big part of this program is that we are formally proving some of the properties, such as the provenance properties I talked about before, described in the architecture, so that the foundations of this are genuinely formally verifiable, and you've got a very strong, secure foundation for your future software. Now, the Morello board will be the only instantiation ever of this prototype architecture. This is very much a research vehicle. We're intending to learn from this, and from this work out what goes into an industrially deployable version of the architecture, into a real future version of the ARM architecture that has got capabilities in. Morello is not that. Morello is only the research vehicle, and there isn't compatibility guaranteed between what we do in research and what happens in the future. The concepts will be compatible, but there isn't going to be binary compatibility. So what is the Morello board? It's actually a pretty high-end computing platform. Quad-core, bespoke CPU with this prototype architecture. The CPU is based on the Neoverse N1 core, which is the same one as in the AWS Graviton G2 devices. It's showing up as being a highly performant core, multi-issue, superscalar device with 3 levels of caches. There are 4 of them fully coherent, all built on a 7nm process running at around about 2 GHz. Alongside that, we put on a GPU and a display controller such that this platform will be able to run server workloads and client workloads to allow experimentation in different market spaces with different software workloads. It's got PCIe C6, it's SPSA compliant, it contains 16 gigabytes of memory. So this is a pretty high-end machine, as shown in this block diagram here, which in the interest of time I'll actually skip over. But it's no good just providing this hardware. We're also providing software and tools so that people can make use of this and concentrate their research on, well, how do I use capabilities? What can I do with this new technology? So it's going to come with a tool chain initially developed around LLVM, but we're also going to release a GNU set of tools, and then a series of operating systems: FreeBSD, Android, Windows, PE, Octo, Debian, Red Hat Fedora, and SUSE will all be developed so that people don't have to port different operating systems onto this themselves. They can start using capabilities in those contexts. The timescales of this, well, it's already been running for a year and a bit already. We've got, we're going to have a software model of the Morello board out by October this year, in just a couple of months' time now, which will allow the initial development of software, and the architecture specification of this prototype superset architecture will be released at the same time in October. And then by December 2021, these boards will be made available. Now, the way people will get access to the boards will mostly be controlled through the UKRI, through their Digital Security by Design program. ARM will have some as well, and some of our main partners are working with them as well. I talked already about Microsoft and Google, and some others will have access to these boards to allow them to be able to do the experimentation we need to take this forward. And what we really want to learn from this are answers to the sort of performance questions and the usability and the software usage models questions that we've got about, is this capability concept worth taking into being the real ARM architecture? What we hope to get are compelling examples of how capabilities are offering security or performance improvements, i.e. either more security at the same performance or the same level of security at a lower performance overhead than what is being used today. Backed up with people using red teams to attack the system and to demonstrate issues and vulnerabilities that would otherwise be exploitable are being stopped by having the capabilities in place. We need to understand how different languages and runtimes can make use of this concept in the context of the ARM ecosystem. And also whether this idea of a fine-grained compartmentalization model really is something that people can make use of and gain value and gain benefit from. If this all works, I actually want this to be a showcase to show other architectures, including Intel's x86 or RISC-V, that this is actually the right way forward for security. Because if this is a big step forward for the security of our software, then it needs to be everywhere. Because if it's everywhere, then operating systems such as Linux and so on can actually rely on it being there and build it fundamentally into where they go forward. We're also gaining experience on what the right SoC hardware will be for that, and we're going to publish learnings from that so people can actually build SoCs around it. And this is all based on a bunch of formal methods and formal proofs that show that this is not just a, yes, ARM says this is okay. We've actually got a formal foundation to the security that we're adding. And at the end of the day, what we really will want to learn from this program is what to put into the ARM architecture in the future to support capabilities based on the learnings from this innovative and exciting Morello project that we've pulled together. So we're very much hoping that many people will be able to participate and make use of this, and I hope you guys are as excited as we are about where this could go. Thank you very much.
My name is Robert Watson. I would like to talk to you today about how we got from CHERI to Morello, a story of architecture, software, and research. I'd like to acknowledge my co-investigators, Simon Moore and Peter Sewell from the University of Cambridge and Peter Neumann from SRI International, as well as a large host of research engineers, PhD students, and postdocs, without which CHERI would really not be what it is today after the last 10 years of research. I'd like to acknowledge our sponsors, especially DARPA, for their extraordinary support over 10 years. More recently, UKRI, including Innovate and EPSERC, ERC, and a number of industrial sponsors, including ARM. So we will briefly talk about the CHERI architecture, the transition from CHERI into Morello, our Morello adapted CHERI software stack, and also sort of past, current, and future research directions around CHERI and Morello. If you want to learn more about CHERI, do visit our website, chericpu.org, and take a look in particular at our technical report, An Introduction to CHERI, released last year. So what is CHERI? Well, CHERI is the product of a large research program between SRI and Cambridge over 10 years. It is an architectural protection model. What that means is that we have taken ideas about capability systems and merged them with contemporary hardware and software. We've added new security primitives to the instruction set architecture. These are implemented by the microarchitecture in the processor. These enable new security behaviors in the software stack. So CHERI is focused at mitigating vulnerabilities, in particular in the C and C++ trusted computing bases. So we recognize that type-safe languages and managed languages are great ways to write software, but we cannot help but notice that your hypervisor, your operating system, and often the language runtime itself, your type-safe language, are written in C and C++. So we are there, we hope, in order to help you with their vulnerabilities. We really have two pitches, fine-grained memory protection and scalable software compartmentalization. We will talk about both. But the goal is to directly impede the exploit techniques used by attackers and to mitigate broad classes of vulnerabilities, even unknown future classes of vulnerabilities. It was a project in hardware-software semantics co-design, so we have a set of architectural interventions to mitigate vulnerabilities. This means introducing new features like tagged memory, a new hardware capability data type, but we've tried to be sympathetic to current hardware and software designs, processes, operating systems, C and C++ languages, programs. We imagine that you will deploy new hardware and that will let you incrementally deploy these features in software. And by co-design, we mean we start off by modifying the instruction set architecture, which we model formally. We apply this to a set of instruction set architectures, originally MIPS, now RISC-V and ARMv8. We have a set of formal models about which we can perform security proofs, instruction set emulators, multiple FPGA prototypes, complete software stack, including compiler suite and linker and debugger, full MMU-based CHERI BSD operating system based on the open source FreeBSD system, C and C++ language applications that are all open source. And because it's co-design, we do this over and over again. We evaluate for performance, for security, for compatibility, and we iterate, modifying the hardware, the software, the formal models, and so on. So I told you 10-year research schedule. Well, that's quite a bit of time. What have we done? Well, the first couple of years, we're actually building a research platform. In 2010, there was not an open source instruction set architecture and open source hardware that we could just work with for what we needed. So we had to build our own. We then spent several years exploring how capabilities might interact with a RISC instruction set architecture, especially an MMU-enabled one. We were then able to push our gaze a little bit more towards the software stack, so both for compilers and operating systems, all co-designed, so modifying the architecture, the hardware, and the software as we went. Then turned our attention for the next 3 or 4 years to really efficiency, large-scale software evaluation and adaptation. And then most recently, a transition to RISC-V for our research platform, which is essentially complete now, work on temporal memory safety, formal proofs, and other related topics. During that time, we published technical reports and instruction set architecture about every 1 to 2 years, a series of papers, none for the first couple of years, which is a long time. She's an academic. But since then, about 15 papers describing various aspects of our work on CHERI and more in the pipeline to come. But concurrent to a lot of that, from about 2014, 2015, was a large-scale collaboration with ARM. We had ARM engineers on site many days of the week at the computer lab in Cambridge, regular meetings with software teams, hardware teams, technical management, and so on, culminating last September in the announcement of the Morello board. Morello is a project supported by UKRI here in the UK and by ARM, and also a set of commercial partners to build a large-scale experimental prototype integrating CHERI support into ARMv8A. So in a couple of weeks' time, the instruction set architecture from Morello will be released along with an executable model for public use. We will open source along with ARM and Linaro large-scale software stacks for use on Morello. And in 2021, the board itself will ship with the CHERI-enabled CPU system on chip on an evaluation board. So let's talk briefly about what CHERI is. So CHERI is an architectural protection model, as I said, part of the instruction set architecture. And our goal was to deconflate two ideas that are mixed up in the world of memory management units, and that's virtualization and protection. So memory management units protect based on address or virtual address. CHERI is going to protect based on references, the pointers to addresses, and these are complementary approaches. In general, when we do protection, we need some form of indirection or a lookup table. By piggybacking on pointers, we avoid adding new indirection and lookup tables, which are common additions when adding security to the architecture. This is greatly simplifying, although it comes with some implications. CHERI is an architectural mechanism that enforces policies arising out of software. So sometimes we look to language level properties such as the C and C++ languages and their memory allocators and their linkers, the operating system. Other times we need new software abstractions. For example, if we compartmentalize a process, we now need a new abstraction for a compartment because those don't exist in operating systems today. CHERI capability extends an address. It is perhaps used to implement pointers or other things in your software stack. Tags protect integrity and the valid provenance of capabilities. Bounds constrain where accesses go. Permissions control what operations are allowed architecturally. And we have a set of further features to support software compartmentalization. We merge these into your register file. We extend the existing registers much as 16-bit was extended to 32 and 32 to 64. Well, this is 64 to 129. We also support tagged memory. So these are non-trivial interventions in the architecture. We have a set of system extensions as well, which extend exception handling, page table entries, and so on to support some additional protections we need. This is the model in Morello. It's the model in CHERI RISC-V. It was actually not quite the model in MIPS. In MIPS, we had a separate capability register file. We transitioned to the current model as a result of research that really showed that the impact on low-end microarchitectures was quite substantial in terms of control logic to having multiple register files, mattered much less in high-end microarchitectures. I told you over 10 years, we're approaching our 8th version of the instruction set architecture, shifting from theme to theme, enhancing our approach. And in ISA version 8 will be synchronized with Morello. It will be, the same functional footprint that appears in ARM's instruction set. But we can revisit the history of our ISA by looking at it in terms of collaboration with ARM. Since 2014, 2015, a lot of our work has been focused around problems raised during ARM's exploration and their customers' explorations of CHERI, around energy use, around performance, around code compatibility, the development of compressed capabilities, shifting to an architecture-neutral protection model, trying to eliminate exceptions from domain transition, a whole host of work really motivated by these types of conversations, and also not just architectural work, but microarchitectural work to support this architecture. So what's coming in ISA version 8? About a year and a half's worth of work. A number of experimental features are no longer experimental. We have new work in temporal memory safety, some modest work in the area of C language semantics, performance improvements, and so on. But perhaps most importantly, as I said, this is the version that synchronizes to Morello. When you want to learn about Morello's protection features, its motivations, descriptions, and rationales, do take a look at CHERI ISA v8, which explores those topics in some detail. Just thought I'd mention, one of the interesting things we've done along the way is to formally model all of our work on instruction set architectures, MIPS, RISC-V, and now also Morello, and prove security properties of those instruction set architectures. You can take a look at the paper on this. It was at Oakland, which is the IEEE Symposium on Security and Privacy in May of this year. What about microarchitecture? Well, here's an example processor, 3-stage pipeline, very simple design, extended for CHERI. We add new operations to allow capability manipulation and management. We tag the existing registers. We carry around tags in the data cache. We have a tag controller, a DRAM, in order to store tags in DRAM, which has not been extended for tags. And all of this motivates some research. So we had a paper at ICCD in 2017 looking at how to implement tagged memory efficiently without changing your DRAM. Lots of interesting trade-offs here. Do take a look at the paper. The primary performance optimization point was actually energy use, DRAM access. Also work on how to compress capabilities. We had a 256-bit architectural capability in our early designs to allow software exploration. Now we have a set of semantics. We spent a lot of time optimizing them, trying to get them down to 128-bit, which makes a big difference in terms of cache interactions for pointers. What about software? Well, one thing we can do, I told you, is to implement fine-grained memory protection. And roughly speaking, what we do is we say, well, why doesn't the compiler implement its pointer type using capabilities? And now all the protection properties of capabilities apply to pointers, subject to compatibility, of course. The integrity and provenance validity properties prevent pointer reinjection. They prevent pointer corruption. This allows us to have temporal memory safety and mitigate a whole range of attacks. The bounds allow us to provide spatial memory safety, but also impact temporal memory safety. Monotonicity, which we've not talked about a lot, allows us to prevent privilege escalation, allows us to build sandboxing. So we can do a lot of different things using these architectural primitives. And of course, it's a co-design project. So as we add architectural protection, we adapt the compiler to use these features. We have to ask questions. If there's valid provenance for pointers, we have to know where the pointers come from. If there's integrity, we have to know how they move around and how to maintain integrity. If there's monotonicity, we have to know software can play by those rules. Lots of questions that have to be answered through large-scale prototyping. And what we've done, in fact, in the memory protection model is protect a variety of aspects of C and C++. We can protect language level properties. We can take the sizes of allocations to stack allocations or heap allocations to functions and so on. But we can also protect the language runtime itself, the got pointers implementing global variables, return addresses, control flow, and so on. These mitigate vulnerabilities in C and C++, but also exploit techniques lower in the stack. Roughly speaking, what we can do in this world, where we deploy the CHERI features in this way, is take the graph of pointers that hold an application together, both the explicit ones and the implied ones, and implement these in capabilities, giving them capability-based protections, as long as our memory allocators and our runtime linkers and so on suitably describe the policies they want in terms of the architecture. We have a paper on this work at ASLOS 2019, CHERI ABI, which explores the whole operating system implications of using memory safety in user space applications. Another paper at IEEE Symposium on Security and Privacy this year, looking at temporal memory safety. How do we prevent use after free vulnerabilities on heaps reliably and quickly using CHERI? Another thing I mentioned that we could do with CHERI is, of course, software compartmentalization. So we have these graphs of pointers, which are now graphs of capabilities. Capability injection is not permitted. Bounds are restricted. They can't be broadened. This means that if we limit the registers in the register file in terms of capabilities, we can also limit the accesses. We can build efficient isolation. We can also build efficient sharing, which allows us to build efficient compartmentalization. So what is possible with this? Well, we have more compartments, more frequent domain transitions, more efficient memory sharing. All sounds great. We can sandbox web browsers and mail applications, but it also raises a lot of research questions. In particular, what should the software operational model be? Because these are not processes, these are something else. So we've been exploring different operational models. Just like an MMU, CHERI supports many different ways to use it. And also many questions, how are they created and destroyed? What is the message passing primitive? Is it function call based? How does debugging work? And so on. We've really been exploring two models, one based on sandbox libraries within a process and another using CHERI to implement process separation so that we can use CHERI sharing between the processes. Both of these models will be available on our CHERI BSD Morello operating system. And finally, perhaps the transition process. So we've been working closely with ARM since 2014. We've had ARM folk in our buildings, common meetings, meetings with customers. It's been actually really great. It's been a very exciting project. It has only become more exciting since the advent of Morello. We had to do a lot. They tried to figure out how it integrated with contemporary rich instruction set architecture, contemporary microarchitectures, the business interactions, whereas we focused on, what does it mean for CHERI to be architecture neutral, compiler backends and compiler front ends, OS internals, and so on. We made a lot of improvements to both the architecture and the microarchitecture. How does capability compression work? How does tagging work? Domain transition, temporal safety. Working through the software stacks, understanding the implications, looking at larger applications, doing more work on formal modeling and proof, solving a lot of practical problems, building demonstrators, evidence, collaborating to try and show whether CHERI improves or perhaps hurts performance or security in various situations. So ISCF, Digital Security by Design, is a really interesting thing. This is a UK government-funded program which is in part supporting the development of Morello. There is significant industrial match from ARM, but also companies like Microsoft and Amazon and Google to build a demonstrator board, apply the CHERI ideas to a high-end microarchitecture, to demonstrate the ideas in hardware, to allow software developers to engage with them better. It's hard to engage software developers on an idea where hardware won't ship for, a decade. Right? So maybe we can bring them aboard now so they can start to like or enjoy or perhaps not enjoy all of these things. So very exciting. It's a very unusual board. It is an experimental board, so ARM in many places has built-in science experiments, different ways to do the same thing, so that we can look at them in software and try to decide, what performs best or what gives us the best behavior. So models will ship along with the specification in the next month, and then late next year we'll be looking at board delivery for academic and industrial research. So why is CHERI interesting to ARM? Well, all the pitches I've told you about are good pitches. Memory safety vulnerabilities are a majority of exploitable vulnerabilities today for almost all vendors that we're aware of, the Microsofts, the Googles, etc. The compartmentalization story appeals to companies that are starting to use software compartmentalization to mitigate vulnerabilities. But not surprisingly, they have all the same questions that we do. We've done academic prototyping on small-scale FPGA designs. What happens when you scale up to the real thing? What is the energy cost? What is the performance cost? And so on. These things are disruptive changes. These are best explored through a real experiment. And the Morello board is that, a system that can be, a high-end mobile device or, a medium-end server. It's a great place to do software experimentation, but also evaluate the hardware designs. So we've taken our software designs and have brought them to Morello. Why do we do that? To validate and demonstrate Morello itself, the instruction set architecture, to evaluate the implementation, to allow us to explore all these performance issues, to provide a reference set of software semantics. How should Unix behave? How should processes behave? What are useful ideas about compartmentalization? How should C behave? These are a reference set of designs. But they can also be a template and a prototyping platform, for example, for the industrial partners in the Morello consortium. It can also be a platform for research. So in the UK, EPSERC, like NSF in the US, is going to fund 9 3- or 4-year projects based on Morello, and they're going to need software platforms to work on. So how can we provide them with a rich CHERI-enhanced experience? So we have our DARPA-sponsored prototype software stack for CHERI. There are compilers and debuggers, hypervisors, operating system components with kernel memory safety, with user space memory safety, with compartmentalization, supporting legacy binaries, open source applications like WebKit, Python, Nginx, all available, shipping in the next couple of months with many of these features enabled to run on the Morello models and next year on the Morello board. This hopefully is the platform we need to try and answer a lot of these questions. We've tried to use CHERI in as rich and mature a way as we can. We have a lot of experience doing this. We have software stacks, that have been up and running for 8 years now. But in the end, also, these are fundamentally incremental deployments. And there is a great research space of less incremental deployment of CHERI ideas in operating systems and compilers and languages. Thought I'd just handwave briefly some of these EPSERC projects. Working in language virtual machines, looking at accelerators, looking at the semantics and formal properties of CHERI in programming languages, compartmentalization, a host of research topics that I think are really interesting and hopefully will be enabled by software stacks and boards like Morello. So just to wrap up, where do I see future research directions? I see a lot going on. We don't have good answers to questions about, if you design new software today with CHERI in mind, what would it look like? right? As opposed to incrementally changing your current software. How should CHERI interact with language runtimes and just-in-time compilers that not only have quite severe and interesting performance concerns, they're already concerned with pointer sizes being too big and we just made them bigger, but also we want to ask questions about the vulnerabilities that exist in compiler-generated code and JIT-generated code. Does CHERI help them? Does CHERI not really make a difference? We just don't know until we do this research. We could use CHERI more richly than we currently do. We focused on memory safety, but there's a lot of attacks that actually really relate to type safety in C and C++. And there might be the opportunity to use CHERI to help with those at some trade-off around performance, security, compatibility. We're very interested in managed languages. Could we support sandboxing of native code associated with those languages? Could we be a better communications interface between different managed language runtimes? Could we accelerate managed language runtimes? We don't know. They're all research questions. How does this work with hypervisors and virtualization? How does it work with debuggers and tracing? If we tell you should compartmentalize software, can we write tools to help compartmentalize software, to analyze the benefit, to reduce the implementation cost? And of course, how do we evaluate the impact of CHERI and Morello? Lots of questions to be found there, hopefully lots of interesting answers. So just to wrap up, CHERI primitives were really developed over 10 years of hardware, software, semantics co-design. They appear to successfully enable fine-grained memory protection, scalable software compartmentalization, and they will appear in an actual ARM board starting late next year in a high-end processor design, industrial quality implementation, which is very exciting. This will run our complete open source CHERI software stack, as well as code arriving from companies like ARM, Linaro, and others. And we think there are a lot of opportunities for research. The research is definitely not over. What are CHERI-enabled software models? What architectural and microarchitectural improvements could take CHERI further than we've managed to take it? So do take a look at our website, chericpu.org. Take a look at our technical reports, including our instruction set spec, also our introductory documents. Welcome any questions you have and conversation and discussion. Great to talk to you about all of these topics. And hopefully many of you will get a chance to try out Morello in the coming couple of years. Thank you very much.
This talk is going to be a quick overview of several interlinked research projects. So these are collaborations between the University of Cambridge, ARM, various other places. As you can see, there are lots of people involved in this. It's several big collaborative projects. So let's talk about architecture. So the ARM architecture, it's the center of the ARM ecosystem, as you know, the specification of the allowed behavior of hardware and the basic assumptions for software development. But, as you also know, it's large, 8,000 plus pages, and really rather complex. And historically, it's not been altogether well defined. Like other architectures some years ago, especially the concurrency models were really not very clear. And historically, also like other architectures, it's been a purely prose and pseudocode document, not mechanized in any way. And that means it's only usable as documentation, not directly for testing or for analysis or proof. It has been a book. I should say that the technical work that I'll talk about here will be focused on ARM v8a, although much the same could be done for ARM-M. So these collaborations that I'm talking about, these are aiming broadly at making it possible to specify and test and reason formally about the architecture. So to convert it from something which is purely a document to something that has which is a precise mathematical and computational artifact. And there are three parts to this I'll talk about. One is the instruction set architecture, the other concurrency, and the third verification of security properties for the Morello prototype architecture, which is adding CHERI features for hardware security. ISA then. So this is the sequential behavior of instructions, but by that I include all of the complexity, so decode, address translation, and so on. So as I said, this was historically described just in pseudocode, and ARM transitioned internally a few years ago to mechanized ASL. And what we're doing is we automatically translate that ASL into SAIL. So SAIL is a domain-specific language that we've developed specifically for instruction set specification. And it has open source public tooling. You can just download it. It's a simple, reasonably cleanly designed language, imperative, first order thing. It's got some lightweight dependent types so that you can statically check all of the bit vector computation that is pervasive in ISA descriptions. And then, most importantly, it has nothing else. It's a simple language, it's got simple imperative semantics. That makes it good for analysis. Moreover, the behavior of memory is really not described in Sewell. That's left to an external memory model, and that one lets one plug Sewell definitions into various tools for relaxed memory concurrency. So from Sewell, we generate multiple artifacts. So you see, in fact, we have a range of ISA definitions specified in Sewell, and from those we generate automatically all these yellow things. So we generate emulators in CNO-CAML, we have work on test generation, we generate tools that can evaluate the allowed behavior of concurrent code, and we generate theorem prover definitions for SMT and for Koch and Isabel and Hall 4. So this Sewell ISA semantics, this thing up here, so this includes everything in the ARM ASL, so floating point, page table walks and so on. And this kind of complete authoritative architecture description has not previously been publicly available for any architecture. It's quite big, it's about 100,000 lines of specification. So one should ask, is it correct? Well, for an earlier version, we tested it against the ARM internal architecture validation suite, and it passed the same number of tests as the ASL model. Is it usable for sequential testing? Well, the Sewell generated emulator for ARM, it goes at about 200 kips. That's certainly not blazingly fast, but is usable for operating system boot, so we can boot Linux and the Hafnium hypervisor and other such code. Is it usable for proof? So we've proved, for example, a characterization of address translation, which is one of the most hairy parts in Isabel, and along the way that also found some small bugs in the ASL. Still pretty intimidating to work with though. If you look even just at the simplest instruction, so this add instruction, that takes many pages and many auxiliary definitions in the ASL to precisely specify its behavior in all cases. And the load and store instructions are much longer. So what we now have is a tool, ILA, which is a symbolic evaluator for Sewell. So you can use that to take that authoritative instruction semantics and specialize it with respect to some specific constraints on opcodes and architectural state. So you might, for example, look at this add instruction in EL2 with some specific page table configuration or what have you. That doesn't actually matter for add, but whatever. And after a bit of simplification, that gives you this very concise description. It reads a register, it does bit vector arithmetic, and it writes register. And we've got rid of all of the detail which is only needed for other cases. Okay, let's switch gears now and look at the concurrency. So many hardware optimizations, as you know, especially out of order and speculative execution, so these are carefully designed and implemented to be unobservable for sequential code, except of course for performance effects and side channels, but that's another story. But these optimizations, they have significant effects on the behavior of concurrent code. If you use concurrent context, you can observe what's going on in quite some detail. So that raises the question, what can concurrent programmers actually depend on? And if we go back 10 years or so, ARM, like basically every other architecture, didn't have this very well defined. Right? And as a result, partly of our collaboration with ARM and with various other people, we now have well-defined, precise formal models that capture the architectural intent and that do define in computable ways the allowed behavior of any user mode concurrent program. So these models are in several styles, but they're proved equivalent, so you can use whichever is the most convenient, and they have quite different characteristics. One is an axiomatic model, so this is a predicate on complete candidate executions. That's concise, and a text version of this is what you find in the ARM, but it's a teensy bit inscrutable. Then if you want a bit more hardware intuition, if you want to see how these phenomena arise from out of order and speculative execution, there are abstract microarchitectural operational models. And these you can also execute incrementally. You don't have to come up with a candidate execution to check. And then finally, sort of in between those two, there are what's called promising operational models. So these don't have the hardware intuition exactly, but they're still incrementally executable. For each of these there are tools. So the herd tool of Algarve and Maragé has existed for a while, as has our RMEM tool for these operational models. What's new now is that we have Euler axiomatic, which lets one use axiomatic models on examples that might involve the full ARM ISA, because this uses the Sewell ARM v8a instruction semantics and this Euler tooling that I was just describing. So one can take, say, a concurrent litmus test, just in ARM assembly, and an axiomatic model, and the tool will compute the set of allowed executions of that litmus test. It's a web interface, you can just click on it, try it and see. The RMEM tool has a sort of similar web interface, except now the interaction is that one can step through the allowed transitions of a possibly out of order execution, or one can exhaustively search them. That's user concurrency, load, stores, dependencies, barriers, atomics, that kind of thing. But what about the interaction of concurrency and all these systems features of self-modifying code, of exceptions, interrupts, address translation, and so on? So this is still very much work in progress, but we have this paper by Ben Simner and other that looks at the first of these, right? Self-modifying code and iCache decache maintenance. And this is also supported by that Euler axiomatic tooling, so one can take a litmus test that now might involve self-modifying code and iCache and decache instructions and an axiomatic model that's been extended to cover all of this and compute the allowable executions of that litmus test with respect to this model. Finally, for the third part, let's look at CHERI. So CHERI is a set of architecture extensions to support hardware-enforced fine-grained memory protection and secure encapsulation. And the way it does that is using supposedly unforgeable capabilities. So the idea is that this is something that would let one take existing highly vulnerable C and C++ code bases and with relatively little effort execute them on with software and hardware that guarantees that not all security problems are absent, nobody could possibly do that, but that guarantees that many kinds of security problem can't arise. And basic idea then is that the hardware has capabilities. So if one takes some piece of crappy C code like this that has a bug, all C code has bugs, if you run this in ISO-C, then, well, technically it's undefined behavior, but if you run it on an implementation, there's an exploit. In CHERI-C, this pointer value is not just a virtual address number, but a structure with address and base and permissions, and a hardware managed tag bit that tells you whether it's valid or not, right? And that tag bit can't be forged. So that's guaranteed to trap. So CHERI was initially an academic project, started in 2010 with Robert Watson, Simon Moore, Peter Neumann. I came along a bit later, and it's done a lot of work on hardware design, software design, architecture design, and so on. Right, so that's produced many academic papers, it's all great. But is that enough evidence to demonstrate that it's feasible for mass market industry adoption? Well, not so far. Right? But so this Morello project is developing a prototype architecture and an evaluation board, real silicon, that aims to do this. Right? So this will give us something, and ARM, something that one can use to demonstrate that these performance and adaptation costs are reasonable, even on a full-on industrial scale implementation, a high-performance implementation. This is funded in part by the UKRI Industrial Strategy Challenge Fund Digital Security by Design project, which we were involved in instigating. So, I say CHERI guarantees these security properties with supposedly unforgeable capabilities. What does that mean even? And how can we possibly know that this architecture specification, which is 8,000 pages long, does indeed do these? Well, what we can do is use the Sewell infrastructure that I described at the beginning and various theorem prover machinery to do machine-checked mathematical proof that specific precise properties always hold. And we also, although I don't have time to talk about it here, we use Sewell for various lightweight rigorous engineering things. So not doing formal proof, but using the formal models as a primary reference for the documentation and for testing and for test generation. So these security properties then, they look like this kind of thing. So these are properties which hold for arbitrary code in any machine state subject to the preconditions of the theorem. So this one, for any intra-domain trace, so for any execution up to the point of a security domain boundary crossing, the reachable capabilities from the final state are no greater than those of the initial state. Or this one, for any trace that starts out within a properly set up compartment that cannot affect the memory of anything else, and it can only exit the compartment in controlled ways. So these are proved by Kindle and Nienhaus for CHERI MIPS in Isabelle. So these are guaranteed to hold of the architecture in the form of the Isabelle model, which is automatically derived from, in this case, the Sewell model. In this case, the L3 model. What we're doing now is the same kind of thing, but for Morello, for the full-scale adaptation of ARM to support capabilities. And in the course of that, one has to nail down some sort of essence of CHERI properties that characterize what an arbitrary CHERI instruction can do. Right, so I think I'll skip over that. But so what we're developing, and what we should soon have then, are Isabelle proofs of that these properties do hold for Morello, and that they imply those previous theorems. And also using the same infrastructure that I've described, checking using SMT and Euler of a number of other properties, and also test generation that target interesting capability tests. So all these we've initially had for CHERI MIPS, we will have them for Morello coming up soon. So machine-checked mathematical proofs of security properties of full-scale industry architecture. Of course, this will not guarantee that everything is correct. It doesn't guarantee that the hardware implementation is correct. Software can still be wrong, but it means that the fundamental architecture will not be wrong in these ways. So this has all been pretty brief. If you want more details, here are various papers, links, and so on. These Sewell itself and the models you can just download from GitHub. These tools, they have web interfaces. Do try them and use them. And with that, thank you.
All right, welcome everyone to our Q&A session. Thank you to our speakers. We've got them all here. First, we'll let them introduce themselves. So, Richard.
Hi, I'm Richard Grisenthwaite, ARM's Chief Architect.
Thank you. And now Robert.
Hi, I'm Robert Watson. I'm a reader in Systems Security and Architecture at the University of Cambridge.
And finally, Peter.
And I'm Peter Sewell, also at the University of Cambridge.
So thanks again to all three of you. We've got some great questions for the audience. We'll head right to those because we've got a short time to talk about a massive effort with some significant results. So first off, do you have any estimates on the performance impacts yet?
I'll make a start at this, but I'm sure others will be able to comment. I mean, to a certain extent, the whole reason we're doing Morello is to get performance impacts, and to get a proper way of measuring them. And as I think I alluded to, it really depends on which of the usage models you're talking about. If we're just talking about the basic memory safety that you can get out of Morello, then it's kind of a function of how many pointers you've got in your code. So if you run some of the benchmarks that are pretty sparse on pointers, then frankly, the performance impact is negligible, 1 or 2% or whatever. If you end up with something that's very pointer rich and some of the managed languages can have this property, then it can go north of 10%, we think. But your mileage varies greatly, and part of the reason we pushed the whole Morello program is I actually got rather fed up with this question, because it's a building block for a lot of different ways of solving the problem of different problems. You can get all sorts of different performance costs, but you can also get performance benefits if you start using the compartmentalization. Use it to create compartmentalization in that situation. You can avoid, as I talked about before, abusing the process model. I think Robert's got some thoughts he might want to share with us on that.
Yeah, I think as Richard says, there's a positive performance pitch and a positive performance pitch, opportunity, potentially orders of magnitude performance improvement and compartmentalization. The overhead pitch is we've increased your pointer size, and we already have some experience with the increase in pointer size with the switch from 32-bit to 64-bit architectures, which cause most people a little discomfort and a few people a lot of discomfort. On the compartmentalization question, we accrue performance improvement by potentially reducing context switch times and significantly improving performance of communication. And that's a tricky thing to explore from a performance perspective, because people today craft their compartmentalized applications like web browsers and so on to avoid expensive IP workload and ask the question, what would improve performance? We actually need to ask the question, what if we changed applications to better exploit these facilities, enabling new kinds of security? And we have small case studies, and we look at things, and we do see performance improvements of an order of magnitude or more for small communications across API boundaries, and that's a big deal. I think we need a platform like Morello to answer these questions properly. We need to understand the rich microarchitectural effects. We need large-scale software stacks. There's also, by the way, there's some tricky things in doing the science, right? Compiler optimization is really hard and takes years, and we haven't had years to do a lot of that on CHERI yet. We can drop existing protections that may have overheads, and we don't understand all the impacts of taking those away and how it interacts. So I think we'll learn a lot in doing this. I think Morello is really the ideal platform to start to answer these questions properly, which is a great opportunity.
But that chicken and egg problem that Robert just talked about, which is people currently write software to what hardware is capable of doing, and if we give people radically different things that the hardware can do, then the software can use it differently and get all sorts of different benefits, is really at the heart of why we went down this big step of doing this highly complex prototype, because actually we really want a substrate that people can experiment with, really trying to find out what, if we give you a tool for fine-grained compartmentalization, what can you do with it? What performance wins can you find? And also what things don't work. And the things that don't work, the things that work on paper but don't work in reality, are what this is all about, and vice versa.
Yeah, just to give an example, with web browsers today, no one would think of creating a process for every image that's rendered, because that's just an infeasible thing on today's computing platforms. With CHERI, that looks like it's and yet we can't just estimate the performance overhead by doing the same with processes, because the system will behave so differently. We really need to try it out and see what happens. And that gets into the space of kind of like software operational models, where we now need to think about new programming abstractions in order to support this. And we don't understand how disruptive those are for large-scale applications. It may prove to be straightforward, it may prove to be very difficult, and we need to find out through systems research on top of a platform.
All right.
Shall we?
The next question is about the footprint of this technology. Could we reasonably fit CHERI within an M-class based system?
Again, I'll make a start on this. The way that we're doing CHERI, which is, we go from on Morello 64-bit pointers to 128-bit. Clearly in an M class, that's 32-bit to 64-bit. So you kind of want to do it differently. You've got fewer bits to deal with in the rest of the capability, because I'm not sure the M profile people will thank you to go to 128-bit descriptors. So there are challenges. We have a research program that's independent from Morello, looking at how to do an M profile version of CHERI and to explore that space. It's got slightly different usage models, different requirements. We're doing that separately. We see that if this is a valuable technology, memory safety issues and compartmentalization apply across the spectrum of where ARM works. The reason we're doing the Morello and the A profile is, it's a bigger collection of software that we have to go and work with. It's more complicated, and we really need to understand if it works in those big workloads. The separate activity in the M profile is able to proceed actually in some ways faster, but it's also doesn't require the same level of commitment to do that research. But that is also ongoing. So we're interested in it. We haven't got anything much to say in terms of actually having a product or anything yet.
Yeah, I'll just comment on the general interest in microcontroller space. So we have done some work on 32-bit microcontrollers in our RISC-V based research. I mean, it's early work. It's not 32-bit RISC-V is not an optimized microcontroller architecture. The microarchitectural implementations are very different from what we see in the M-class world. And yet, I think we found, at least in the environments we've been looking at, there is a nice scaling down. There are some fixed costs, and the trade-offs are going to be very different around temporal memory safety, memory access, and so on. Probably the person to ask some of these questions to is my colleague, Simon Moore, who's been leading our microarchitecture work. Say a little about this, now.
All right. This next question is probably for Robert, and that's, do you plan on building a prototype similar to Morello for RISC-V?
Complicated question. So to date, our primary research platform has been 64-bit MIPS, which was the closest thing there was to an open source 64-bit RISC ISA when we started the project in 2010. 64-bit MIPS feels increasingly like it was designed in the 1990s because it was. RISC-V is a more contemporary open source architecture. It didn't exist when we started. We are in the throes of moving a lot of our research efforts over to that. I have a set of open source RISC-V based processes consisting of a 3-stage pipeline, a 5-stage pipeline, and also a superscalar core. But these are research cores. They're open source cores. They're not production quality cores. The superscalar core we're working with Tuber, which is actually based on the MIT RISC-ERO core, is a real superscalar core. It has some features that will allow us to explore all kinds of properties in terms of speculative execution, including the risks of speculative execution. But I don't think it's really a comparable microarchitecture to something like the Neoverse N1. So we will begin to publish work based on, if you want to look to have the complete CHERI software stack up running the suite and so on. So there is the opportunity to play with and dig into this. We have a new version of our instruction set architecture report coming out in a few weeks, next month or so, which has a more mature version of that. If you look at our current CHERI ISA v7, which is what's up on our website, you'll find the MIPS specification and also our draft RISC-V specification, but that predates the entire software stack coming up. So for people who are interested in doing research in the space, we're really happy to talk to you about this.
I would observe that in many ways the results that I think we'll get from Morello in terms of the value of this technology should be architecturally independent. In other words, if this is actually worth doing, the fact that it is worth doing an ARM doesn't mean to say we have to do that, or somebody would have to do the same experiment to find out if it's worth doing a RISC-V. And very importantly, the fundamental IP behind capabilities that we're building into Morello is not being patented, it's being published instead so that other architectures can adopt it. This is a fundamental matter of principle. The reality of the world is that the world's big operating systems need to have not exactly the same features, but a commonality of approach across hardware architectures. And so if Morello ends up proving out that CHERI style capabilities are really worth having, and this is something that needs to go to production, then actually for it to reach its full potential, it needs to be in the x86 architecture, it will need to be in RISC-V architecture. And ARM is perfectly happy with that happening because it will be about adopting a fundamental architectural feature that can be relied upon by the world's operating systems, much as page tables. Everyone's got kind of the same approach to page tables, same but different. I would imagine the same but different occurring around this technology as well. And we're perfectly happy with that. It's actually one of the goals of Morello is to be able to demonstrate that it works on multiple different architectures. Well, at least, sorry, not that it demonstrated it works in the architectures, but at least that the concepts, if they do work, we'd assume they can be adopted by other architectures, and it shows the way for people to do so.
Yeah, I was going to comment on that as well. So, I mean, we started this work off, it was clearly an extension to MIPS built in a very sort of concrete systems engineering style research prototype. But, you know, the cloud in large part, actually, we have the opportunity to take a step back from that, you know, highly integrated view and ask the question, you know, is there a portable protection model here that can span architectures? And the Morello work, I think, and our RIS5 work shows that it really is true. We maintain compiler backends with a common compiler front end. We maintain operating system machine independent code along with a small amount of machine dependent code and assembly. We get the same protection properties. We get the same security properties from the software, we hope, you know, and when we look at these things, you know, the fact that we can have portable operating systems and compilers suggests that we've been successful in coming up with a portable model in the same way as virtual medical, even though the architectural interfaces to MMUs may be diverse across architectures. And I guess one comment there is, I mean, there are some variations between the architectures and how they do CHERI. You know, one key question that came up in the context of Morello was, when are you willing to throw architectural exceptions? So in MIPS, almost any instruction, including arithmetic add, can feel free to throw an exception if it feels like. In the ARMv8a architecture, there's an explicit design choice to avoid, you know, dynamic exception throwing, except in small classes of instructions that, you know, at decode time, what kind of behaviors might arise. And so, and this is a quite specific example, but, you know, whereas we might in MIPS or RIS5 throw an exception when you violate certain kind of capability rules, it's possible to strip the tag and defer the exception that you take into an instruction like a load or a store or a branch where you might throw an exception anyway. We believe that doesn't impact significantly the security semantics. It probably does impact the debuggability semantics. Some care is required in making that argument. I think we need to explore and understand it further. But it's quite exciting that there's a tolerance for quite different stylistic and, you know, deep design choices, instructions, and architectures, while still getting a portable software model that can be relied on by programmers. I mean, other than in low-level runtime bits like runtime linkers and so on, there's almost no architecture-specific choices relating to CHERI and high-level application software, where there's CHERI modifications that's portable across the architecture, which is really an exciting thing to say.
All right. The next question is, to what extent, if any, will the microarchitectural details of Morello be available to independent researchers?
We're not going to publish the full microarchitecture of the newer version 1, which is, as been discussed, a commercial core. What we are prepared to publish are sort of capability essential microarchitectural techniques, i.e. anything that we discover that we really see there aren't alternative ways that microarchitectures, a typical out-of-order machine, could approach this problem. So at that point, if we didn't make those sort of things available, then you would have a situation where here's an architecture that anyone could do, but in order to be able to build it competitively, you would have to have that secret. And we're committed to ensuring that even microarchitectural approaches, if there aren't any seriously viable alternatives, we will publish those and make them available. But we're not going to provide all of the microarchitecture details because, as I said before, this is based on a highly realistic and deployed commercial core, which does have some of our know-how in it. And I don't think my colleagues at ARM would be at all happy if we gave that away.
Right. The next question is, what are the main challenges of utilizing capabilities within self-modifying code in managed runtimes for languages such as Java or JavaScript?
I can take that question. I think we actually review these problems as maybe through two main lenses. Lens one is the structure of code generation and code execution fundamentally changed by CHERI? And the second one is, because managed language runtimes are so performance sensitive, to what extent do you have to adapt your performance optimizations to allow for the changes that are implied by CHERI? So with respect to the former category and memory safety, really the structure of code is the same. There are load instructions, there are store instructions, there are stack frames, there are things that look like GOTs that point to globals and so on. So on the whole, we find that code generation doesn't enormously change. The details are spelled a bit differently and so on. The main disruptive thing that happens is this requirement for provenance validity. Pointers have to come from somewhere. And so we're no longer allowed to embed addresses and materialize them from instruction streams, right? We have to derive them from other capabilities. And this could cause some change in the behaviors of language runtimes and code generation. It's not clear to us these are enormously disruptive, but I think until you run these experiments on real-world large language runtimes, you're not really going to understand the trade-offs there. When it comes to compartmentalization, something you'd want to do for language runtimes, and we know that JITs and so on are sometimes sources of significant vulnerabilities, especially when combined with use after free vulnerabilities, for example. Getting code into execution or arbitrary code into execution is a popular way to compromise web browsers and systems. Those are the kind of things we want to do in compartment. We don't understand the implementations of compartmentalization on language runtimes. I mean, we've done some early work on aligning Java native code interface work with sandboxing and found that to be effective, and sort of carrying some of the Java style protections over into the native code as a result of compiling CHERI, which is an exciting and interesting thing to do. But I think some larger experiments required to answer that question. So the other aspect I said was the change in performance, and because language runtimes are so performance sensitive, right? It's really if you look at sort of improvements in JavaScript runtimes, a lot of the focus is on, I can run this set of benchmarks with more rich set of workloads at a much higher speed to allow JavaScript to be used in ways it couldn't otherwise be used. It is the assembly language of the World Wide Web, for better or worse. We see some potential issues. Language runtime authors often optimize for pointer size. Even on 64-bit architectures, they may use 32-bit or 36-bit pointers. We see language runtimes that compress larger pointers into smaller integers for precisely this reason. They bumped into this performance overhead with the data cache as they went from 32 to 64-bit. To use Richard's language, they probably wouldn't thank us for now turning their 64-bit pointers into 128-bit pointers. And the trade-offs change on optimization almost certainly, whereas compression of pointers in language runtimes for 32-bit targets, gives them an address space trade-off. Can they name as large heaps and so on? For us, there's also a security trade-off. So we can imagine using 32-bit and 64-bit pointers alongside CHERI capabilities. The architecture is designed for that. But these pointers, small integer ones, won't have integrity protections, won't have bounds. So there's a trade-off around protection on JavaScript heap objects, for example. These are great research topics that we would like to understand more, because I think what we see happening is, as with 64-bit deployment, there's a hybrid deployment of the CHERI ideas to get back this performance. And therefore, there's a trade-off space which is much more interesting. So I think there are lots of opportunities, but I think there are real challenges we need to try to understand better.
I would observe that one of the research programs being funded by UKRI or EPSRC under the Digital Security by Design program is actually looking at using Morello as a target for Java and JavaScript. And so, there is research going on. It's one of the areas that we really want to see lots of real research going on to explore the trade-offs that Robert was talking about.
Yeah, Morello creates an opportunity that has not existed for our other architectural research platforms. Neither MIT nor RISC-V is well known for having highly optimized language runtimes. And they may, well, probably not MIT, but RISC-V may well grow them in the future. But if you want to do that kind of research today, the only place, or in the next year, the only place to do that will be Morello.
Moving on.
All right. So due to time constraints, we'll limit ourselves to 2 more questions. But any more questions, feel free to email them to me, Nick Spinelli, and I'll get them answered somehow. My email address can be found in my areas of interest section for my profile on this platform. So second to last question is, Robert, on slide 13 of your presentation, you mentioned minor C language semantic improvements. Can you expand on that?
Yeah, I mean, so we clearly affect the semantics of C, and we do it in a few ways. So one of the things we like to say in a positive way is that we shear off some undefined or implementation-defined behavior that arises when you break the C language memory safety rules, in as much as they exist. So, the execution of arbitrary code, not a defined thing in the C language specification when you overflow a buffer, and yet a very popular thing. What we want to be able to do is assert strongly those bits of undefined or implementation behavior now have defined behavior in some form, and it's a complex set of trade-offs there. So in that sense, I think we're quite helpful. But there are other areas where, for example, we at least choose different interpretations for example, the behavior of casting between integers and pointers and storage of pointers. And this can lead to compatibility concerns. So one of the aspects of our work has been trying to really minimize those while also retaining some of the strengths of the architecture and the C language compilation model. Speaking of sort of the EPSRC-sponsored research areas, UKRI is funding at least 2 projects in the space of looking at the impact formally on language semantics. And my expectation is that we will see some continuing evolution there. CHERI and Morello, right? They're an architecture that can be used in many different ways. And one of the aims for Morello and for CHERI RISC-V has been to ensure that that architecture could be used to implement different C language semantics so that over time we can hone our approach and try to solve problems better. And I expect that we probably will.
All right, so our last question is a high-level one that we won't be able to address fully, but that's for all of you, and that's, are you worried about the software adaptation part, given that it has often taken quite a long time for past technologies of much lower complexity, for example, point authentication codes or MPX, to be adopted by compilers and kernels?
Well, I can give a very quick answer, which is yes, but being slightly more fulsome. Yes, actually, that's why we're doing Morello. I mean, the normal way of deploying architecture is you just build it into the next generation of the processor. You know, we introduced exactly things like PAC, you know, just as a regular tick on the ARM architecture. The trouble with that is that the learning from it and the understanding from it then trickles over something like a 5 or 6 year period as the silicon gets out and then people start making use of it. And it was very clear that given how big a step Morello could be, or how unusual and different this technology is, that just sort of tricking it out and hoping we'd learn about it in the normal way of things wouldn't work. So the whole rationale behind the Morello program is to get some of our, you know, key partners, you know, people like Microsoft, people like Google, who have both stood up and said that when this thing gets built, we will actually do dedicated research into making use of this technology to understand it, to give us the feedback. And so that when we, assuming it all then shows some value, then when it comes to being able to properly put it into a production architecture, or put in the learnings to that into production architecture, we've got a head start in the learnings as to how this is expected to be used. It will be much further down the road than would be the case if we just put it out in the regular way. So the simple answer to the question is yes, we're worried, and that actually was probably the number one motivation of doing this very unusual step of doing, you know, an industrial scale research vehicle rather than just putting into the architecture in the way we've done other things.
Yeah, I'll maybe add my thoughts there as well. I mean, the challenge in designing CHERI was we want to be as disruptive as possible, yet still adoptable. The more disruption we're willing to accept, then maybe the more we can improve the status quo. The more disruption we do, the harder it is to get the world to adopt it. And I think we still don't quite, I mean, I guess we're very successful in like right being on that fine line where you can't quite tell if it's adoptable, but at the same time, you're able to provide, you know, a significant improvement in security, actually pretty good compatibility. So there's a set of trade-offs. So I will say, you know, a significant effort went into at least supporting the ability to run, you know, legacy binaries in conventional ways, continuing to support MMU-based operating systems. A lot of our design choices are around maintaining the status quo while having these very selected interventions in the architecture and the microarchitecture. And for capability systems, which have chosen to be much more disruptive in their effect on software. I guess we'll see how it plays out. I mean, all of the conversations we have with companies are engaged around this transition question, and it will be very interesting to see how the next couple of years go. One thing I think that also differentiates our CHERI work from a lot of the other work is, at least recent research work, is the size of the research software stack that we built on top. You know, we have, you know, large modifications to operating systems and compilers and significant experience making them. ARM will release a modified version of the Android operating system that uses some of these features as well. We need those kinds of validations at scale. They help us understand the degree to which we, affect compatibility. They also give us the opportunity to improve as we work through the research program.
All right, we'll do one more question for Peter, even though I said we were done. That's about the formal proofs. How have you analyzed the translation from the actual model to the formal model?
So I guess the question is really, how have we validated that translation? What grounds do we have to believe that it has anything to do with the original? And we did a couple of things. So one of our colleagues then inside ARM, Alistair Reed, took the formal model that we've produced and ran the entire ARM architecture validation suite on it. So this is, in some sense, well, one of the definitive references of what it means to be ARM, and the translated formal model then satisfied the same number of tests, quite large number of tests, that is, as the ARM internal model. So that gives us some grounds for confidence. And then we additionally, we routinely have booted Linux and other operating systems above the formal model, which has not previously been possible for any other. So the translation is not proved correct, but the result is pretty much as trustworthy as the original.
All right. Thank you, Peter. And thank you all. Thank you, Richard, Robert, and Peter, for your presentations and for your time in this discussion. We appreciate you sharing this work.
Thank you very much.